towering spectacularly over West London. The biggest single-span arch in the world. Visible for 21 kilometres across the city.
Beneath this record-breaking arch is the most expensive sports arena ever built, Wembley Stadium.
But this extraordinary architectural feat owes much of its glory to some surprising engineering connections. A crossbow.
God, that's got some shove, hasn't it?
A rock climber's knot.
I remember I used to have arms.
A 19th century glider. A fake gold crown and Archimedes' most famous principle.
I'm not just walking on water, I am running.
And stealth aircraft.
How did all those make this spectacular stadium possible? When almost £1 billion is spent replacing a world-famous stadium, you'd expect to be impressed.
Underneath that vast arch hangs a giant 11-acre roof that covers 90,000 seats.
Each seat has perfect views of the immaculate turf. And no worries if you're caught short. There are 2,618 lavatories, more than any other stadium.
Impressive, but rebuilding the home of football pushed the architects and the engineers to their limits.
One of the biggest challenges was to make every one of the 90,000 seats feel like the best in the house. They had to be spacious, comfortable, sheltered, and each one with the perfect view of the pitch. And that meant no obstructions. Things like columns supporting the roof.
The solution involved building a massive arch that would hold up the roof from above, so no more columns. Norman Foster, one of the world's leading architects, wanted to build an arch that would stand out on London's skyline. But not just any arch. It was going to be the largest single-span roof structure ever built.
Not only had this never been tried before, but as this was the rebirth of an icon, the eyes of the world were on the aesthetics as well as the engineering.
At 133 metres tall, Wembley is the only stadium in the world to have beacons for low-flying aircraft. And with a 7.4-metre diameter, the arch is wide enough to drive a Eurostar train through.
But building the arch wasn't the only problem. Getting it up there was no walk in the park.
The engineers at Wembley faced a dilemma. They couldn't use traditional cranes to raise the arch. At 1,750 tons, the weight of 10 jumbo jets, it was just too heavy. The answer to their problem lay in a mountaineer's knot. And the first connection brings me to the bottom of a cliff.
Just stick it on a figure of 8.
Climbing instructor Chris Hurley takes me through the paces.
Okay, we need to attach it to 2 points.
Okay, that's okay.
You enjoying that?
No. This knot is going to be an essential part of whatever it is we're about to do.
Yes.
Is it going to be supporting any weight?
It's called a Prusik knot, invented in 1931 by Austrian mountaineer Dr. Karl Prusik.
Sit down again.
Yeah, please.
In theory, a couple of these knots are going to take me up this sheer cliff, with the ropes taking all the strain. Me just looking good in that hat.
Now, Chris, how do these knots actually work?
Okay, basically, you create a lot of friction on the rope. I've got one here, which I'll just put on and show you. Take the loop, put it around the outside of the rope. You then pull the rest of the loop on the inside of the larger loop that you've just created.
Yeah.
And then you do that again on the inside.
So does every climber know how to tie one of these?
Well, I should hope so.
Yeah.
Okay?
And the effect of that is a lot of rope
from the support rope in contact with the other rope.
Yeah,
So
absolutely.
there's a lot of friction between them. So as soon as you put the load on, that's a lot of rope in contact with the rope. It's a lot of friction. It'll hold the load. It sort of locks itself, doesn't it?
It does. It just locks up on itself, yeah.
Friction stops me falling. But to heave myself up the cliff, I need 2 of these knots working together.
Tuck your foot in behind you a little bit.
Yes.
Now stand up on that nice and straight. It'll take a lot of the effort out of
I'm
it.
there again. Right. So that's the whole point of this system is it's got 2 anchor points.
Yes.
The lower one, the higher one.
Yes.
And at any given time, the load is supported by one of them.
Yes.
At this moment, it's the top one.
Yeah.
Slide the other one up to it.
Yes. And then you just, it's
And
a
then we do another
continuous
advance.
process. So you just basically repeat the process again and again.
Has anybody ever raced this?
Not with prusik knots, I shouldn't think.
Importantly, these knots provide a secure way to climb a free hanging rope, making them lifesavers for mountaineers.
These knots, then, what are they supporting?
That your full body weight.
All of me on the...
Yeah.
Chris, this isn't really so much rope as string, is it?
Yes, it's very thin rope.
It's okay, I was saved, but, you know, I'll be saved.
The process may be simple, but it's slow and very hard work.
Not easy. It's
Not
just
by any means.
It really would have to be an emergency before, frankly, I could be bothered.
This is the hard bit up here.
What? You mean the rest of it hasn't been? I can certainly see, as a system, it's just brilliantly clever in its simplicity. 2 points, moving, advancing slowly up the rope. One thing you can't deny is even with just me on the end of it, it's a lot of work. Not the gripping, not the friction, that's easy.
Yeah.
But advancing, moving on each time.
One knot is always locked while the other one slides up. And this is the principle the engineers at Wembley would find crucial for lifting their arch. They had to make sure the arch wouldn't crash back to Earth during the lift. So they attached metal cables to the arch as it lay on its side. But they would need something stronger than string knots to pull it upright through 112 degrees.
Enter the engineering equivalent of the prusik knot and a huge power source doing the work of my legs. They're called strand jacks, and it took 25 of them 4 weeks to raise the Wembley arch.
It was a mammoth lifting task requiring 130 kilometers of steel cable. All this cable ran through these stationary strand jacks. I've got Mike Wade, the engineer responsible, to show me just how these strand jacks make use of the simple climber's knot.
Mike, I understood how the prusik knots worked. I'm struggling to see the link between those and this, which is a strand jack.
OK. Well, what I've got here is an anchor, which is the equivalent of our prusik knot. And this is a piece of strand, which is the equivalent of the climbing rope.
Like the prusik knot, it locks if you pull down on it.
So it is doing the same job as the knot. It's going one way, it's gripping, and then moving and advancing and gripping.
Exactly. So at Wembley, the arch would have been over there, and what we're doing is we're pulling this way to pull the arch up.
Inside the jacks, metal anchors work in pairs, just like the prusik knots. One is fixed whilst the other is moved by a piston. As the piston moves, the anchor grips the strand and pulls it through. Then the piston moves back with the anchor, while the fixed anchor grips the strand and takes the weight. The whole process repeats, slowly but surely. And this allowed engineers to raise the arch by 5 degrees a day until it was in position.
It's still grip, move, grip.
That's correct,
move,
yes.
grip, move, grip, move. It's
Yes.
the same process. It's a giant prusik knot.
Exactly.